Good afternoon, everyone, and welcome to the October edition of the PitchD, the PhD speech, organized by the IEEE student branch of Politecnico di Torino. I am Giovanni Amedeo Cirillo, and I'm a treasurer of the IEEE student branch of Politecnico. And today I have the pleasure of being the presenter of this event, where 3 PhD students from our university will present their research activities, who are related to the domains of electronics for biomedical engineering, analog design, and digital design. Well, before starting, some observations for those who are following this event on our YouTube channel. First of all, in a few minutes, you will have a form for that could be compiled in order to receive the certificate of attendance to this event. But I would like to remind to everyone that the certificates will be recognized only to the PhD students of the program in Electrical, Electronics and Communications Engineering. On the other hand, and probably it is also more important, in order to create a debate for what concerns the contents that will be presented by our guests, I would like to remind that you can provide your questions directly in the live chat of the YouTube streaming. Well, I think that we can immediately start. In order to do that, I would like to invite our first speaker, Noemi Giordano, to turn on her webcam and her microphone.
Good afternoon, everyone.
Her presentation is entitled Multi-Source Phonocardiography for the Home Prevention of Heart Failure. Noemi was born in Pinerolo, Italy, and she received her master's degree in biomedical engineering from Politecnico di Torino in 2018 with the thesis, Feasibility of an Analysis of a House Device for the Prevention of Heart Failure. She worked as a researcher under grant from January to October 2019 at the Biolab laboratories at the Department of Electronics and Telecommunications of Politecnico. She is currently a PhD student at Biolab, and her research is mainly focused on the design of devices with application in cardiology, cardiological signal interpretation, and telemedicine. Now, Noemi, it is your turn, and thank you for your presentation.
Okay, thank you very much, Gianni. And wait, I started from the end, and that's not nice. Okay, here we go. My name is Noemi Giordano, and I am a PhD student in bioengineering and medical surgical sciences. And today I will introduce the problem of home prevention of heart failure and a possible technological solution based on multi-source phonocardiography, which is the object of my PhD project. So, in my opinion, every engineering project should be triggered by a problem in real life. So the first question here is, why heart failure is a problem? So let numbers talk. Heart failure is a chronic disease which affects 600,000 people in Italy, only in Italy. And from the clinical point of view, it has a very high prevalence and a very high mortality. So if you have just a glimpse, you can think that 1 out of 5 people aged 40 today will be diagnosed with heart failure in the future. And the 50% of that people will die in 5 years from the early diagnosis. So this has also obvious economical and logistical consequences for the healthcare system. It was estimated that the annual expenditure of the Italian healthcare system related to heart failure is around 2 billion euros. And the main cost is related to the hospital admission, which lasts averagely 5 days and is estimated to cost around 10,000 euros per admission. So the hospital admission will be strongly reduced if the acute episode of heart failure could be prevented. because if the heart failure is prevented promptly, then the hospital admission could be avoided. And the problem is right now that there is no efficient and prompt technological solution available on the market for home prevention of acute episodes of heart failure. In the clinical context, the diagnosis of heart failure is performed through either echocardiography, which is an ultrasound imaging exam, and or through blood test by the analysis of peptidic natriuretic peptides called NT-proBNP. So it is evident that both these exams are not suitable for home monitoring because they either need a skilled technician or physician or blood test, which obviously cannot be brought home. On another side, multi-sensor platforms were tested for the prevention of acute episodes of heart failure, but typically they rely on very non-specific parameters such as blood pressure or weight, and so they have a very low reliability and a very low predictive power. So the aim of the methodology I am presenting today is to increase the predictive power of multi-sensor platforms, but without losing in usability in domiciliary applications. So this methodology is based on simultaneous recordings of electrocardiogram and phonocardiogram. Phonocardiogram is a representation of the mechanical behavior of the heart because it consists of the electric recording of R sounds. R sounds are acoustic waves, mainly generated by the closing of R valves. In particular, in a common phonocardiogram, two main R sounds are present, and there are the first R sound, which represents the closure of atrioventricular valves, respectively the mitral and the tricuspid valves, and second R sounds, which is generated by the closure of semilunar valves, which are the aortic and the pulmonary valves. Both these events are triggered by an electrical stimulus, which is the ventricular depolarization, which can be seen in the corresponding electrocardiogram as a QRS complex. So heart failure is a chronic condition where the electrical stimulus cannot be translated effectively to the mechanical action. So the problem is not at the electrical level, but it is at the mechanical level. So the heart is not capable of pumping the blood into the system anymore as it should be, and so it cannot provide the right amount of oxygen and nutrients to the tissues. So concerning the signals, what we can see is that the electrocardiogram of a patient with heart failure is comparable to the one of an healthy subject. But concerning the mechanical activity, and so the phonocardiogram, the heart sounds of an heart failure subject are delayed with respect to the ones of an healthy subject. And so this methodology is based on this concept. If we are capable of measuring the latency of our sounds with respect to the corresponding electrical ventricular depolarization, then we are able to catch delays and to prevent heart failure, monitor and prevent heart failure. So the first step of the project was the design and development of an algorithm for the estimation of the latency of our sounds. This takes as input the electrocardiogram and the phonocardiogram and filters them, and then the R wave peaks are detected within the electrocardiogram and used for the segmentation of our sounds within the phonocardiogram. This occurs on the envelope of the phonocardiogram, which is calculated using the Shannon energy of the signal. And in particular, the main novelty of our algorithm with respect to other state-of-the-art algorithms present in the literature is that we are capable of detecting not only the two main R sounds, but also the contribution of the single cardiac valves. And this is important because that allows for not only the detection of heart failure, but also for its classification. So here, for example, in the signal, you can see the output of this phase, which is the time of closure of each cardiac valve. So in order, the mitral, the tricuspid, the aortic, and the pulmonary valves. Afterwards, for each component of each R sound, the latency with respect to the corresponding ventricular depolarization is computed. And the performances in the detection of our sound components is as high as 99.2% in terms of sensitivity and 100% in terms of specificity, and this outmatches other state-of-the-art algorithms. So to validate our algorithm, we use a recording system made of one commercial recording system for biomedical signal, which is called Remotus, which we equipped with an active probe with electrodes to record a single channel electrocardiogram, and a microphone probe, which is based on a condenser microphone sensor and is shaped as a stethoscope head. In this way, we were capable of recording signals from 25 healthy subjects. Before in the first stage, we wanted to characterize the value, the typical value of the latencies over the healthy population. Of course, to get proper characterization with a statistical significance, a larger population would be needed. But in this case, this analysis was very important for us because the topic is very novel and no data was provided in the literature. So we wanted to know what to expect from an healthy subject and to understand what was at least temporary normality range for each cardiac valve. Afterwards, we used the same methodology to follow up patients with a history of cardiopathy and with past acute episodes of heart failure and past hospital admissions for heart failure. So here you can see the variation of the latency values for each cardiac valve over the time. And we could find a qualitative correlation between the latency values which we measured and the actual health status of the patient. So if you look, for example, at the blue line, which represents the mitral valve, you can see that in some moments, it is the most constant among the valves, but in some moments there was a tendency to increase, which typically culminated with a hospital admission or a variation of the therapy, which took the value lower again. So the main problem of the recording system I presented up to now is that the recordings were performed at the patient domicile, but by an expert user, because the patient could not perform the recording himself. And why? Because it's not easy, actually, because that recording system is not really suitable for a home care application. The problem mainly resides in the positioning of the microphone. And the problem, we can say it's two-sided. On one side, you can see from these plots that recording the signal from different points of the chest means obtaining signals with very different quality. And the best auscultation point is not fixed because it mainly depends on physical parameters which are vary from subject to subject, and they are unpredictable because, for example, they are related to the heart position and orientation, which are different from subject to subject. So a skilled and experienced user is needed to obtain a signal with of sufficient quality. On the other side, you can see that if we apply our algorithm for the estimation of the latency of our sound components to signals recorded at different points of the chest, we obtain different results. And this further complicates the problem because in phonocardiography, a standard positioning as exists in electrocardiography, for example, in phonocardiography it doesn't exist. So here is where multi-source phonocardiography comes in, because the idea here is to move the problem from the positioning phase to the processing phase. So instead of using a single microphone, we decided to use multiple microphones and then find the best strategy to use these simultaneous recordings in the processing phase. So we tested some approaches, and a first approach, which is simple but effective actually, was signal selection. So we chose a quality matrix, like for example, signal to noise ratio, and then we selected the best signal according to the quality matrix, and we applied our algorithm for the estimation of the latencies on it. Another approach is the signal enhancement. So we used array signal processing techniques like beamforming to combine the original recordings into a single signal of enhanced quality. And I did that by means of the estimation of the delays among the signals, which we did through maximization of the generalized cross-correlation function. And then I compensated those delays by using delay and sunbeam forming. A more sophisticated approach that we tested and that gave promising results actually was Blindsor separation. So this approach is based on the assumption that the recordings, that the signals we can record over the subject chest are mixtures of uncorrelated acoustic signals generated each by a different cardiac structure. So for example, the left heart, the right heart, and a general other thoracic acoustic noise. So what happens in the thorax is actually matrix multiplication by a mixing matrix A, because depending on the path that each acoustic source has to do to reach each microphone, it is filtered and amplified differently. And so the Blindsor separation approach tries to estimate the unmixing matrix, which is the inverse of the mixing matrix, to recover the acoustic sources as they were emitted from the cardiac source. So once we have those estimate of the real acoustic signals, we can have a more reliable estimation of the time of occurrence of the closing of each cardiac valve. Why? Because before we detected all the cardiac valves contributions on the same original recording. In this case, we can detect the mitral and the aortic contributions on the left heart signal and the tricuspid and pulmonary contribution on the right heart signal. So to conclude, I introduced the main problems related to the usage of phonocardiography in the prevention of acute episodes of heart failure. And my research is going in the direction of using multi-source phonocardiography to solve the problem of the expert positioning of the microphone. So at this stage, we are designing and realizing a system based on multiple microphones and completely suitable for domiciliary use. And at this stage, we are realizing a prototype, which hopefully will be ready in a few months. And in the further future, we hope to integrate our prototype in a telemedicine platform for the home monitoring of heart failure patients. So I hope that my talk was of your interest, and thank you very much for your attention.
Thank you, Noemi, for your very interesting presentation. Now it is turn to read some questions for our question and answer session. Well, let's start with the first one. Is the algorithm computationally expensive? Can it be implemented in an implantable device?
Well, an implantable device is not actually useful in this case, because what we want to avoid is to implant a device, actually. So we want our device to be wearable so that the patient can use it, for example, once a day before going to sleep for 5 minutes, and it doesn't affect that much his own life. Anyway, the algorithm is not computationally expensive, and so it can for sure be integrated on a wearable device which is not plugged, for example.
Okay, thank you for your answer. Let's move on. How much time does the complete process takes?
Sorry?
How much time does the complete process takes?
Oh, very few seconds.
Oh, okay.
The complete process is very quick, like a couple of seconds.
Interesting.
But the processing is not online during the recording. So we record the wall signal, like 5 minutes or 10 minutes of signals, and then we perform processing offline. Okay,
in fact, now there is a question probably related to processing. You anticipated the following question. Let's say this way. Is the phonocardiography processing algorithm for latency estimation implemented in software or is a specific hardware employed apart from the employed commercial biomedical device? I think that it is referring to the device with microphones that you showed in one of the slides.
Yes. This one, you mean?
Yeah.
Okay, well, no, actually this recording system was made for a completely different biomedical signal, but was adapted for our purposes. But anyway, the processing can, since it is offline, at this stage, it was completely software.
Okay.
In the future, we can forecast that the processing will be done at firmware level, but it's not a particular constraint.
Okay, thank you for your detailed answer. There is another one. Can you extract some features, for example, only the peaks before processing the data, or you need to record and store the entire signal?
Well, I don't really think it's needed for this application, but for now we prefer to record the signals because we are still in a research phase, and so we would like to have the signals to perform other activities on it in the future. So for this particular algorithm, maybe only the detection could be, only the detected peaks could be sent out as output, but we prefer to record the signals so that we can have them for further research.
Okay, there are not other questions. So I would like to thank again Noemi for a very interesting presentation.
Thank you.
And now it is the turn of Roberto Rubino from the Electronics and Telecommunications Department of Politecnico, and he will give a speech entitled Relaxation DAC, a new concept interface for the Internet of Things. Roberto received the Bachelor of Science degree and Master of Science degree in Electronic Engineering at Politecnico di Torino. He is currently carrying on his research as a PhD student in Politecnico di Torino as part of the research activity on ultra-low power, mostly digital integrated interfaces for the Internet of Things. He is an IEEE graduate student member and a member of the Circuit and Systems Society of IEEE. So Roberto, now it is your turn. You can turn on your microphone and you can share your slides for your presentation.
Thank you, Gianni, for the introduction. Okay. I will talk about the relaxation digital to analog converter, which is a new concept interface for the Internet of Things. You know that the Internet of Things is a framework of connected nodes, which is playing a growing role in the market of traditional ICT products. Moreover, IoT sensor nodes are embedded systems which need to be really low cost, very low voltage, ultra low power, and matching insensitive devices. A possible way to target these constraints is to rethink traditional analog design and interfaces so that they are mostly digital, since digital circuits are taking advantage of voltage and technology scaling more than analog ones. This is the framework where the relaxation digital to analog converter has been designed. The IoT interface requirements are low power operation in the order of the microwatt, sample rates in the order of kilosample per second, and the medium-low resolutions for almost all the applications. The relaxation DAC exploits the impulse response of a first-order RC network, which is driven by the stream of bits of the digital word to be converted, which does not need preprocessing. So all the bits are shifted LSB first, and after all the bits have been shifted, the three-state buffer is put in high impedance to hold the capacitor voltage value. If we evaluate the voltage across the capacitor at the end of the n periods, it has the following expression. If we now impose a particular condition on the ratio between the clock period t and the time constant tau, then it happens that at the end of the N periods, the final capacitor voltage, which is the duct voltage, is proportional to the digital input code N, as expected from a conventional DAC. Here we can see an example on 3 bits where all the codes are converted. The features of the relaxation DAC is that there is no need for capacitor matching, unlike for what happens to other capacitor-based DAC, like switched capacitor DAC. So the capacitance can be reduced down to the thermal noise limit, leading to high energy efficiency for conversion. Its simple structure makes it suitable to really low voltage operation, down and below 0.5 voltage. And since accuracy just depends on a single parameter to be calibrated, we just have to meet this condition to have full resolution. It has also an excellent linearity up to the Nyquist frequency, and there is no need for digital word preprocessing. An initial version of the relaxation DAC has been implemented on 40 nanometer technology with 2 sample rate versions, 2 megasample per second and 400 sample per second. Both have been tested on 10-bit resolutions and achieve a really low energy per conversion of around 1 picojoule per conversion. Since the linearity just depends on a single parameter, we can see what is the effect of an error on the clock period on the converter linearity. If an error on clock period is present, we can see that an error step appears on the integral nonlinearity, and this error is maximum always at half swing. This error is also proportional to the relative error on clock period. So this feature can be used to perform a self-calibration, which imposes the equality between the 2 half swing voltages, so providing 1 LSB of maximum error across the whole swing. The self-calibration should thus measure the 2 half swing voltages and modify the input voltage of a VCO, for example, to tune the clock frequency. The proposed architecture is the following, which exploits 2 VCOs based on simple relaxation topologies. The first VCO is used to tune the clock frequency, while the second one is used along with a binary counter as a VCO-based ADC. Both VCOs are driven by the DAC itself by means of 2 pass gates. Well, the self-calibration begins at startup, where the input of VCO1 is 0. So VCO1 starts at its maximum frequency and enables the digital logic to work. An arbitrary calibration word, cal, is loaded and converted, and its voltage value is updated to the input of VCO1 in order to modify the clock frequency. Next step is to convert the first of the 2 half swing voltages. Here we can see the conversion waveform, and the final voltage is connected to the input of the second VCO in order to perform an analog to digital conversion of this voltage. This is performed by enabling the binary counter for each time T-clock redac period, where T-clock redac is the clock period of VCO1. At the end of the enabling period, the binary counter will store a digital word, which is the digital representation of the voltage VDAC of 2 to the n-1. The same procedure is performed for the other half swing voltage VDAC of 2 to the n-1 So its relative digital code is loaded and converted. Here we can see the conversion waveform on 5 bits. And the final voltage value is connected to the input of VCO2 to perform again an analog to digital conversion. At the end of the enabling period for the binary counter will store the digital word, which represents VDAC of 2 to the n-1. So once we have the digital representation of the 2 half swing voltages, the calibration word cal can be updated in order to modify the clock period so that the 2 half swing voltages are the same. Here, for example, we have to increase the clock period to impose the equality of the 2 half swing voltages. So the new calibration word is updated with the proportional value to the difference of the two digital codes. It is converted, and the voltage value converted is updated to the input of VCO1 so that to modify the clock frequency. All this procedure is repeated until the condition of equality between the two housewing code is matched. Here we can see the conversion waveforms across the capacitor at the input of the two VCOs. The input of VCO1 converges to the voltage value which satisfies the calibration condition, the quality of the two housewing voltages, while the input of VCO2 oscillates between the two housewing voltages until they are the same and the calibration is complete. Here it is shown in an animation what is the effect of the calibration on the converter integral nonlinearity. After calibration, we can see that the post-calibration static performance and dynamic performance are improved to provide 9 effective beats and less than 1 LSB on 10 beats of static nonlinearity. A different architecture has been proposed, which is suitable not to an IC implementation, but to an FPGA, mostly digital implementation. The VCO, the first VCO, has been replaced by a tunable clock divider, while the second VCO has been replaced by a voltage to time conversion. All the architecture has been implemented and tested on FPGA by using full digital blocks and some discrete components. Here we can recognize all the digital blocks that we have presented. And the discrete components have been mounted on a protoboard, where we can also recognize all the components which are needed. We used a FPGA board to test the DAC working, and ramp and digital synthesizer have been written in VHDL and synthesized in order to perform static and dynamic performance characterization of different sample rate versions of the DAC. The characterization has been performed by 16-bit data acquisition board. In this animation, we can see that the two housewing voltages become the same. So the calibration is complete. Then a ramp is converted to perform the static characterization of the DAC. After the ramp has been converted, different sine waves at different frequency and different amplitudes are converted in order to perform the dynamic performance characterization. So the different sample rate versions have been characterized by static and dynamic performance, both of them, and they in the end provide more than 12 bits of effective beats and a flat frequency behavior. So this converter has a very high linearity across the whole frequency range up to the Nyquist frequency. The measured result will be submitted on TCAS1, so they cannot be presented here. Thank you for your attention.
Thank you, Roberto. You can your share screen. And I think that now it is time for the question and answer session concerning your presentation. Let's start with the first question. What are the possible applications of relaxation digital tonal converters?
We are targeting IoT systems, as I said. So systems which require really low power operation. And we are actually working on the fabrication of a DAC converter for biomedical applications.
Okay, thank you. We have another question. How much is your redac sensitive to power supply noise? Did you try to implement a differential structure?
Yes. Actually, the redac linearity depends also on the parasitics of the RC network, which is not actually of the first order. They can be compensated somehow. If we use a differential structure, these parasitics are actually reduced. in simulations, since the parasitics of the resistor is split in two and then has less effect on the impulse response of the RC network. It is also, until now, susceptible to supply voltage variation due to this is for the integrated version, since the VCO is currently susceptible to supply voltage variation. But it will be improved by modifying the clock tuning strategy in the next versions.
Thank you for your very detailed answer. Now we have other two questions. The first one is, did you take into account the role of phase noise of oscillators in the DAC process?
Yes, as I told, the phase noise is quite relevant. So in order to have a good relaxation DAC, we must have a low noise VCO.
Okay, thank you. And the last one is, which is the maximum achieved sample rate with these converters?
Until now, 2 megasample per second sample rate in the integrated version.
Okay, thank you. And what about the FPGA version? We saw some
tens of kilosample per second.
Okay, thank you, Roberto. I do not see any other question, so I think that we can conclude the question and answer session concerning Roberto's presentation. I would like to thank Roberto again for his talk.
Thank you.
And now it is the turn of Andrea Coluccio from the Electronics and Telecommunications Department. He will give a speech entitled Logic in Memory Computing, an Architectural Solution to Solve the von Neumann Bottleneck. Andrea Coluccio is an electronic engineer. He achieved his bachelor's and master's degrees here at Politecnico di Torino, and he started his PhD in Electrical Electronics and Communications Engineering last year. His research revolves around innovative architectures and focuses on logic in memory paradigm as a possible solution to the von Neumann bottleneck. Andrea, now you can share your slides and you can start your presentation. Thank you.
Okay, thank you. Okay. I'm sorry, I'm having some problems. Okay. Okay, good evening. Thank you for your introduction. And my name is Andrea Coluccio, and today I'm going to present my research topic, that is Logic in Memory Computing, an architectural design to solve the von Neumann bottleneck. A von Neumann architecture is basically made of two elements that are CPU and memory. CPU is a very fast computational unit, while the memory is slower because of the time required to fetch and store the data. The communication represents a bottleneck in terms of power, energy, and computational time, because the CPU has to wait the data from the memory. In order to better visualize this drawback, here it is reported a graph of the performance of the CPU and memory over the years. As we can clearly see, there is a huge gap that is widening because the memory cannot follow the trend of the CPU in terms of latency. So what can we do to reduce this drawback? A von Neumann architecture is made of these two elements that are very separated from each other, meaning that the memory is read and written very frequently, wasting time and energy in vain. So what if we merge storage and computation together? We get what is called the logic in memory paradigm, in which data traffic is drastically reduced, since the results are already stored inside the memory array. But what does it mean merging storage and computation together? From the literature, we have different approaches to this question, and in particular, we have SRAM and DRAM-based computing, in which we enable multiple word lines at the same time in the memory array, and we sense the potentials on the bit lines that will be proportional to the content of the cells, so it is a kind of analog computation. Then we have resistive memory array computing, in which we sense the currents that will be proportional to the resistance on the path. So it is a quite similar way to compute data as SRAM and DRAM based. And finally, we have hybrid memory cubes, in which we stack multiple DRAM layers on top of each other, and we connect them by means of through silicon bias to a final logical one. So the computation will be performed inside the logical layer. But which kind of algorithm can be implemented in memory? Lima is very well suited for machine learning algorithms. So we published 2 papers in which we implemented 2 neural networks, respectively a fixed point Lima architecture, in which we put a multiplier and a multiplexer for each memory line, and a finer grained architecture that is a binary neural network implementing a XNOR gate for each memory cell. But previous works refers to very specific cases and algorithms. So what we are trying to do now is the development of a fully reconfigurable logic in memory architecture that is made of smart rows. A smart row contains a memory row that performs storage and computation, a series of row interfaces that perform intra-row calculations, and a final output buffer to store the temporary results. By stacking multiple smart rows together, we get what is called the Lima array. And the computation that we can achieve with this Lima array is a single instruction, multiple data, meaning that the same instruction can be executed in each smart row. But which row interfaces are required inside our Lima array? We have 2 possible approaches to this question. And in particular, we have an algorithm-driven approach. So based on the algorithm chosen, we chose the row interfaces. So it is a very specific approach, an ASIC approach. Or differently, we have an algorithm profiling approach. So by studying different kinds of algorithms, we chose the row interface according to the most frequently used instructions. So this is a general purpose approach. Let's analyze the first one, the ASIC one. So considering this very simple example in which we have the computation of the distance between 2 points, if we have multiple points in our dataset, this kind of a computation becomes a force cycle. A force cycle is very well suited for a single instruction multiple data architecture. So it is very well suited for our Lima array. By looking at the main formula of this algorithm, we can determine what are the blocks that are required inside our Lima array. So, for instance, in this case, we have some arithmetic blocks that computes the minus and plus, and the power 2 operator. So our smart row will be composed of an arithmetic row that is in charge of computing the minus and plus, a multiplier to perform the power 2, and the final buffer to store the temporary results coming from the algorithm. Now let's analyze the general purpose approach. For this approach, we defined a methodology, and we applied this methodology for several kinds of algorithms. And this methodology starts with defining the instruction set architecture, that in this case is RISC-V. Then we generate the instruction list with the Gem5 tool. And then we parse these instructions, and we estimate the number of occurrences with C++ and MATLAB, respectively. We executed this kind of methodology for different kinds of algorithms, and we classified them as memory intensive. So for instance, bitonic sorting, Fibonacci series calculations, or write on a file. Computation intensive, so decimal to binary, sorting, random number generators. And finally, miscellaneous, in which we have print on screen, user-defined algorithms, and parsing. So the goal is to move computations inside Lim as much as we can. And the results that we obtained from this methodology are shown in this figure. And if we analyze each contribution one by one, we can find out that there are a lot of memory operations, so load word and store word, that in such a way must be reduced. So in this case are like 23,000. Moving on, we can find out that there are a lot of move operations. A move operation simply transfers data from one register to another one. So it is a very simple operation that can be implemented inside a memory. So by copying one line into another one. So if we can move this computation inside the memory array, we can avoid it inside the CPU. So we can reduce the data traffic between CPU and memory, of course. Similarly for arithmetic operations. Here we have a lot of adds. So sums are very frequently used in the algorithm studied. So in-memory sum could be a very good idea in order to reduce the data traffic and to implement much more computations inside the memory. Then we have branches, but branches cannot be implemented in memory since it is a very difficult operation to be performed. So this kind of operation must be delegated to the processor. And finally, we have bitwise operations that are very, very simple to be implemented in memory. As a conclusion of this discussion, we can say that the Lima array is designed based on the most frequently used instructions in order to execute more calculations inside the memory, and so consequently reducing the von Neumann bottleneck. But designing a Lima array from scratch could be a very difficult task. So what we are trying to do now is the development of a fully automatic synthesis and testing tool that, starting from an algorithm and a library, it is able to provide a plug-and-play HDL containing our Lima array and a performance estimation based on the technology parameters. The tool is called Dexima as Design Explorer for in-memory architectures. The results that we obtained so far for our binary neural network indicates very good achievement in terms of delay and energy compared to a classical von Neumann system. These results are obtained with the CMOS 45 nanometer technology and are very good in terms of delay and energy because of the huge amount of computational units that are working at the same time inside the Lima solution. But of course, this huge amount degrades a lot the power and area. So the results that we obtained for power and area in the case of Lim are not so good. As a conclusion, we can say that Lim is a promising architectural solution to von Neumann bottleneck because it has less energy and computational time required, but also a high degree of parallelization. As a future work, we are trying to develop our reconfigurable Lim architecture, as we said, and our Lim synthesis tool. But also, we want to explore new technological alternatives to CMOS in order to improve the performance that we've shown before, and also to insert Lim in the CPU memory context. Regarding this last point, where could Lim be used inside a classical system? If we consider this very simple scheme in which we have two levels of caches and a final DRAM, the results that we obtain indicates that the memory is accessed a lot. But also there are a lot of misses in the last level of cache. A miss implies a miss latency, that is the latency required to fetch the data from the cache and to put it inside the CPU to perform the calculation. So this latency is completely wasted, and this fact is called miss penalty. But could Lim reduce the miss penalty? So instead of moving data back and forth inside the memory hierarchy, what if we execute a local computation with logic in memory? So what we are trying to do now is the exploration of new architectural solutions in order to reduce the miss penalty and to insert the Lim inside the CPU memory context. Thank you for your attention.
Thank you, Andrea, for your very interesting talk. Just a moment, I was observing that the webcam was too high, let's say this way. Now it is the turn of the question and answer session concerning your presentation. The first question is it difficult to design Lim devices?
Yes, it could be difficult because, of course, not all algorithms are so easy to be processed, let's say. So what we are trying to do, if I can share my screen again, what we are trying to do is to help the designer in the Lim context by developing this tool that is able, from the algorithm, to provide directly the Lim array already configured. So this tool will help the designer in the design phase, starting from the algorithm that can be very complex, for instance, and to obtain directly the Lim solution already configured.
Okay, thank you. Another question is, which are today the main applications, industrial and not, of logic in memory, and which new technologies seem to be promising for this new computing paradigm? I think that it is related to one of the last slides that you...
Yes. Yes, okay. Regarding the technology, until now, our research group focused on CMOS classical technology. In fact, the results that we obtained are not so good because it is not technology directly employable for this kind of solution. So emerging technologies could be a good idea because they are based on a computation that is completely different from the CMOS. So for instance, let's consider MTJ computing or PNML that are nanomagnet logic computing that are very low power. And so they are very well suited for our solution. These kind of solutions are very good because not only performs calculations, but also are can be used to memorize. So the concept of Lim merges storage and computation together. So by using these new technologies, they are able to perform both, so storage and computation. Regarding the applications, there are different applications that can be used inside a Lim solution. In particular, I focused on machine learning algorithms, but there are different kind of applications that are can be, for instance, cryptography or bitmap indexing, or convolution neural networks, and so on. There are a very huge amount of applications that can be used inside the Lean context.
Thank you, Andrea. Now we have another question.
Yes.
Logic in memory seems to be quite close to GPU. Is it possible to do a sort of comparison between them?
Not directly, because yes, they are quite similar, but it is not the only solution to realize a logic in memory array that is a single instruction multiple data computation. This kind of array is the most innovative array that we are developing. But for instance, if you consider the literature, this kind of computation that we use are very different from the literature one, because they use, for instance, Lim to perform bitwise operations, and so to perform very simple operations. The architecture that I proposed is the most the newest one. So implemented a single instruction multiple data, but we can have very different aspects of Lim computation. Let's consider this case, for instance. This is a very specific case. And so it is not reconfigurable, and the computation that we can achieve with this kind of solution is not parallel. Okay, so it is not a single instruction multiple data.
Okay, thank you, Andrea. Now I'm looking for other questions. Okay, I think that there is another one, but I think that you already answered it, but I would like to read it again. Is, in any case, let's say, is Lean design only at the register transfer level, or is it possible to explore this technology at different levels? If yes,
okay, sorry.
I must repeat. Okay, sorry.
Yes.
Is logic in memory only done at the register transfer level, or is it possible to explore this technology at different levels? If yes, in which way?
Okay, Lim is not only related to register transfer level, because it is a very huge project that starts from the highest level, that is the algorithm, to reach the register transfer level, that is the WHDL, of course. So the answer is no. You can move inside from the high level, that is the algorithm, to move towards the low level, that is the WHDL, and so the register transfer level. There are a lot of intermediate steps that are required to reach the WHDL, of course. So from the algorithm, we are developing something that is able to recognize some parts of the algorithms to be implemented inside the memory. So this is purely an high-level approach. Inside Dexima, we have different estimators based on the technology that we've chosen. So also here we have an high-level approach. And then we can move directly to the reconfigurability of the Lim array, that is, of course, a register transfer level. Then we can move directly to the technology, because we have to choose the right technology for the logic in memory, of course. So it is a very complete topic that starts from the most high level to move towards the lowest level possible.
Okay, thank you, Andrea. I do not see any other questions, so thank you for your talk.
Thank you too.
Now you can stop your share screen, and I would like to invite all our speakers to turn on their webcams and their microphones, because we will provide to you virtually the certificates of attendance in order to recognize all the efforts under these very interesting talks. We hope that when this emergency time will end, an event where we can give to you directly, physically, provide to you these certificates will take place. So thank you again, everyone. Noemi, Roberto, and Andrea.
Thank you.
Thank you.
Thank you.
And I would like to invite all people who are following us on YouTube to continue to follow the IEEE student branch of Politecnico di Torino on our social accounts, on YouTube, and so on, because we are going to provide further services to all of you, to all the IEEE community at Politecnico and to Politecnico di Torino itself, let's say this way. Thank you everyone, and hope to see you soon. Goodbye.
Goodbye. Thank you.
Goodbye.